Welcome to the first talk in this session. We're going to have Thomas Würthinger talk about GraalVM from Oracle. So please welcome him.
Thank you. Yeah, so I will talk about GraalVM, our research project to bring code into data. I will first start off a little bit with some of the assumptions we make about things and why we think GraalVM is so important. And the first assumption, and it's the most important one here, is, well, the world is polyglot. This is a diagram from one of the latest TOB index. It's a programming language index. And it shows the programming languages and their distribution. You see there's a lot of programming languages in use. And the one that's in use the most is the programming language called others. There is many, many more languages like hiding in there. So this is kind of one of the first observations here, is that there's a lot of languages out there, and it's not like one language that dominates all others. And the interesting thing still is that like each of these languages has a different virtual machine, like different ways of running things. And this is one of the things you would like to change. When it comes to languages, people often get very opinionated and want to discuss a lot whether this language is better than the other. You can check this out. For example, when you go to Stack Overflow, there is a question called why can't there be an ultimate programming language? And after several weeks of flame war, they closed the question as non-constructive. And that's also not constructive here. I need to stay away from this thing. So yeah, so they closed the question as non-constructive because kind of they couldn't figure out what was the ultimate programming language. Maybe in the future, sometimes in the future it's going to be better. So the thing is, it's not just programming languages that are diverse. It's also the data processing engines are diverse. I just put a couple of logos up there. It's like far from complete. Like the number of data processing engines you can nowadays choose from is tremendous. Like many different. That wasn't me. Many different engines and many different setups. And so the interesting thing there is that you have these different engines, you have these different languages, but you cannot really combine them very well. Meaning, if you run in one of these, let's say you do a query in Spark, yeah, you have to kind of use Scala or some GVM-based language to run your expressions. And some of these data frameworks, including Spark, have kind of recognized that and started. That's kind of annoying. Okay. Anyway, yes, please. So some of these data frameworks have recognized that, and like Spark, for example, has introduced something called Spark R, where they combine R with Spark in some ways. But if you look at it closer and see how they actually combine things, it's not very tight combinations. It's like R is still running in a separate process. So you use Spark kind of to scale some of your operations, but then the R runtime is again running in isolation from the rest of the world. And so when you look at the typical application structure, you have data layer, you have middleware, you have client side. I have here some example of technologies in use in these layers. And there is some issues with such an architecture. There's some challenges with such an architecture. And that includes things like, well, there's a lot of round trips from client to middleware, round trips from middleware to database. There's a lot of latency that's hidden in those round trips. And what usually happens is that then people start to realize, okay, my round trip to the database is a problem, from middleware to database, for example. And then the solution to that is, well, let's put a cache into the middleware. I've seen some application architectures where then the middleware has like, I don't know, a 10 gigabyte Java heap and caches all sorts of data just to avoid going back to the database. And the other problem with such an architecture, of course, is, well, you have different languages, meaning if now I want to actually put some logic into the database, I will need a PL/SQL programmer. If I put some logic into middleware, I need a Java programmer. If I put some logic on the client, there's a JavaScript programmer. So it's different languages, different tools, but also kind of a certain amount of overheads from caching and latency and so on. So, and this is something with GraalVM we want to change, because we want to be able to run those languages in all of those layers without kind of having to choose the language because I'm running in a specific layer. Well, people like languages, and some languages, in particular like Node.js, for example, have a very rich ecosystem of modules. This is taken from a website called modulecounts.com that shows the main package managers of various languages and how they're increasing. Node.js at the moment is increasing a lot in numbers. So it's an incredible amount of modules added per day. And people go to these languages, or for example, want to use Node.js because of that rich ecosystem. So they do want to reuse a lot of logic that's already written by others, and it's very efficient. I was writing a Node.js application a couple of weeks ago, and I was writing like about 15 lines of code, maybe 20, and I was throwing in like about 10,000. And that's kind of not unusual, that you would, in your application, have about 10,000 lines of code that you kind of pulled from the internet that is doing some functionality that you reuse, and then you kind of glue it together. That's very efficient, very productive for a developer. It's also a certain security problem, because all of the code that you're throwing in here is untrusted code, and nobody's going to review that. And I think everybody who says that he's reviewing all of his Node.js dependencies before he's running the application is a liar. So not going to happen. So, and interestingly enough, there are some issues already in the Node.js community around this, where, well, there was some article from 1 year ago, August 2017. Yeah, malicious code in the Node.js npm registry, because somebody was placing some malicious code there. And, well, it doesn't seem like there has been a solution to that so far, because I think about 5 days ago is the latest virus in ESLint. This is from 5 days ago, where somebody was putting a code into the most popular JavaScript checker, like style checker, and that would steal npm credentials, right? Because when you, for example, if you install a Node.js module or if you install a Python module, you're effectively running untrusted code with practically unlimited privileges on your machine. And somebody was able to sneak in some malicious code there. So that's a big challenge in this environment of having a lot of third-party models and having a lot of third-party reuse. And that's why we think with GraalVM we also want to address that. So to summarize the 3 aspects that you want to address with GraalVM, the first one is we want high performance and standardized tooling for all languages. So we recognize languages, there's a lot of languages, it's very polyglot. We want to have the same performance for all languages to get so you don't have to choose the language based on performance. And the second aspect, you want to have standardized tooling, because maybe an even bigger challenge than the performance aspects is that, well, if I want to use JavaScript, I need a different debugger than if I use Java or PL/SQL. So you have a different debugger, you have a different profiler, you have all different kind of things you need to learn as a programmer if you actually want to use more than one language at the same time. So that's one thing. Second thing is you want efficient embeddability in diverse environments. This includes data stores, databases, or data processing engines like Spark, Flink, Cassandra. And the third aspect, what GraalVM tries to achieve is to have an ability to execute these languages in a secure sandbox execution environment, so that you can run untrusted code on your machine and don't need to worry about it. Maybe you need to worry about some Intel bugs. That's separate talk. But other than that, yeah, at least a reasonable amount of security, so people cannot immediately read all your files when you run npm install. So these are the 3 pillars, and I will in the talk I will kind of quickly skim a little bit over what we do for each of those. So the first one I will go fairly quickly over because we have been talking about GraalVM and this aspect quite a bit. We have like 2 research papers on that where we show how we achieve this high performance for all languages. And to just quickly explain it in 2 slides is the way we execute the languages is the languages are written just as normal interpreters. And those interpreters are specializing interpreters, so they capture profiling feedback from the application. So in this example, I have here a language that's a JavaScript, and I have here a plus operation, and then I want to know whether the plus operation was a double operation, an integer operation, a string operation, or something else. So that an interpreter is specializing itself. But then, of course, you might say, well, if you're running interpreter, like this is going to be slow. And to kind of mitigate that, what we do is that we take the interpreter. Once it reaches a stable state, we take the interpreter and then create compiled code automatically from it. So the important aspect, and that's the difference to current architectures, is that our compiler is completely language agnostic. So our compiler doesn't know anything about JavaScript, doesn't know anything about Python or Ruby or whatever, and can still execute those languages. All of our language-specific aspects are only in interpreter. And that's very different to other runtimes out there, let's say V8, that's specialized on JavaScript, where JavaScript-specific parts are almost across the whole stack. So what we do is to kind of create this compiled code, but because JavaScript is a dynamic language and we cannot prove, for example, that the operation will always be an integer, what we need in our system is something that's called de-optimization, meaning once our integer assumptions break, then we need to be able to go back to the interpreter, re-evaluate how the program behaves. For example, here, overflow to a double. And once the tree stabilizes again, we do another compilation. And that's the typical cycle of JIT compilation, where you do profiling, optimization. If you're unlucky, de-optimization, profiling again, optimization. And the unique thing about GraalVM here is that the whole process is language agnostic, and all of the semantics is in the interpreter. And that makes it easy to implement languages on top of GraalVM. And we demonstrated that by implementing a lot of languages on top of GraalVM. Well, of course, GraalVM is a Java-based compiler, so it can run Java-based applications like Java, Scala, Groovy, Kotlin. But it also can run JavaScript competitively in performance. It can run Ruby. We have a Ruby interpreter. We have an R interpreter for the R statistical language. And we have a Python interpreter. So all of these languages are implemented in a way that they run with high performance, but the core runtime, the core compiler doesn't know anything specific about those languages. In addition, to get a little bit broader, we implemented an LLVM bitcode interpreter as well in this system that allows us to execute LLVM-based languages. That includes C, C++, Rust, and others. And maybe in the future also Go if there will be an LLVM backend to Go. So GraalVM can run those languages, but more importantly, it can run those languages in the context of other engines and environments. The default environment that we would run in is OpenJDK, which is the Java platform. So you can run those languages on the Java platform. But we also can run those languages in the context of the Node.js platform. So we have an embedding of Graal into the Node.js platform. We can run GraalVM in the context of the Oracle database. We have a prototype of that online for download, where you can run this embedded in the Oracle database. We can also run it embedded in MySQL. That's to show kind of the embeddability in data stores. And finally, we can run GraalVM also standalone if you want a microservice with fast startup and low footprint, and you don't want to associate it with any existing runtime. You can also just run kind of Graal just in a Docker container or with Kubernetes. So that's the overall picture of the GraalVM architecture, of the languages we currently support, and of the embeddings we currently support. I say currently here because our vision for GraalVM definitely is to go beyond what is on this slide. We would like to support even more languages and encourage third-party researchers, and language implementers to use GraalVM as a way to implement their language. And similarly, we would like to encourage third parties to embed GraalVM in their system and in this way make their system extensible. Because the nice thing is that you can now mix and match. You can basically say, okay, I want to run Ruby in the Oracle database, or I want to run Python on MySQL, or I want to run R on OpenJDK. So I can choose a random embedding and a random language, and I can make my own environment how I need it for my application. So this efficient embeddability, I would like to talk a little bit about why GraalVM specifically is designed for that. And the main thing here is that the GraalVM runtime supports a complete separation of physical and logical layout of any data structure. So when you usually, in Java, for example, have an array access instruction, you have an array access bytecode, then the runtime makes a lot of assumptions about how that array is actually looking like. So the runtime will say, okay, I will look at the header and plus I will add 16 to it. This is my length field. I will multiply that by 4, and this is my index. So the runtime has a lot of assumptions about the data, how it's coming in when an operation is performed. GraalVM doesn't do that. So in GraalVM, all of the operations have something where they have the ability to adapt to a new data layout coming in. So the operator would ask the operand how to access it. So when you have an array access in GraalVM here, it would check, well, do I know the data structure? If I do not know the data structure, it allows the data structure to give the access pattern. This is interesting because it allows you to run logic with different data structures and not depend on the exact data structure the runtime needs. And it allows you to keep data in compressed formats or custom formats without creating objects from them, copying all the data over to run some logic in JavaScript or Python. To give you an example here, a very simple example, I have here a method that's defined in JavaScript that calculates the area of a rectangle, and it just accesses width times height. I can call this, of course, from JavaScript with the same language, but I can also call it from another language. So I can define my rectangle data structure in Java with a different layout than JavaScript would have. And then I can call the same logic with a completely different data structure. But this just doesn't work only between languages. It also works between the GraalVM execution and its embedding. And I have here an example, like from a database embedding, you can then for example, have a select statement that selects width and height from a database table. And instead of creating the objects, the data goes directly to the area function. And the area function can operate on the data without actually creating JavaScript objects. And this is important to not only support like a specific database format, because databases have different formats, row-based, column-based. It's basically your choice as an embedder how you want to present the data structure to the running engine. The other thing GraalVM supports is inlining across language boundaries. So in current systems, if you, for example, have a native model like written in C, and you call that native extension from Ruby code, like there's no way those things are going to inline. We are inlining across these boundaries. So we can inline across any two languages that GraalVM supports. Because for GraalVM, it's just, well, I have a couple of ESTs of those languages that I'm executing, and I can just combine those ESTs together. This can lead to huge speedups when the boundary between, for example, C and a guest language is important, or when the boundary between two languages is important. And this inlining really, it basically shows that there is no overhead at all to work with these two languages at the same time. Generally, there's also no overhead when you give a data structure from one language to the other language. So we avoid copying on any boundary, but allow the data structure to flow over the language boundary. We allow the data structure to just go to the other language, and the other language recognizes that this is a data structure from a foreign language, but can still access it efficiently. These are kind of the core values we put into the system to allow language interoperability to be very fast. So people don't need to worry about that part, and to allow embeddability, to allow you to have your custom formats of your custom network buffer, for example, and expose this network buffer to the running application without actually creating objects. I have here like a little demo that I have here in a screenshot for the sake of time. Is with GraalVM, you can write an application, for example, a Node.js application on the left. This is Node.js using Express. You run it, but you can use Java data steps. So you can use Java mods big integer here to have a big integer representation, an efficient one. And you can also write code that will run some R code. In the demo on the left, which has a little bit more complex R code than on this code, but on the demo on the left here, it shows like one example how this can be useful is where you use R to plot a diagram, an SVG, and then you return that SVG from your Node.js application. That's just a little toy demo to show how languages can be potentially mixed. In practice, of course, we are not saying like people should generally mix languages, the more the better. But there are scenarios, in particular with mixing, let's say, Java and a dynamic language, or C and another language. There are some scenarios where this can be very, very useful. So on security side, we want secure sandbox execution for GraalVM. So one of the things we put in to achieve that is to allow to securely run native extensions. So one problem you have when you are running, let's say, a Ruby application is, okay, I have the Ruby code that's managed, but then there's a native extension that's running C code. And that native extension running C code is potentially malicious. So in order to also safely execute that C code, we have a mode of GraalVM where we safely execute LLVM bitcode. So we kind of simulate the memory model for C instead of actually doing all the direct access. This can be useful also for C code that's in generally critical, because our simulation avoids any type of typical security problems with C, like buffer overflow or use of the free type of bugs. So these bugs are all gone. And the performance impact of having all these additional checks on your C code is rather small. So it's like maybe 10%, 20%, depends on your application. And the reason for that is that our system is kind of designed for profiling and JIT compilation. So our system is designed already to avoid these overheads. Like JavaScript engines or Java engines generally are very good in avoiding array bounds checks and overheads with safety checks. And we can leverage that for our safe execution of C. We have some time boxing when you want to embed a certain script in your application, so you can do time boxing. But not just time boxing, you can also do memory boxing. So you can also avoid the problem that scripts that you don't trust might cluster the memory. One important aspect of our system is that we want to reduce the amount of code that needs to be trusted. And in our system architecture, the language implementations themselves, like the R implementation, the JavaScript implementation, do not need to be trusted. That's very different from the current R implementation or the current JavaScript implementations. Those implementations are typically written in C, C++, and all of that code is has potential for security vulnerabilities. We achieve this, that we don't need to trust the language implementation, because our system has sort of one additional layer. Every program in computer science can be solved as one additional level of abstraction. And we have one of those. So if you look at, so typically what would be, like this is the new layer basically. Like usually you would have the OS layer somewhere, you have the virtual machine, and the virtual machine runs the guest application. That would be typical layer. But in our layer, the virtual machine doesn't directly run the guest application, it runs the guest language implementation, also in managed mode, because our guest language implementations are all written in a managed language. And only that guest language implementation is then running the guest language application. And this means that both of those layers do not need to be trusted. So I can run a GraalVM language in a secure mode where even if the language implementer makes a mistake or puts in some malicious code, it cannot break out of the sandbox. So this is very important for us, because if you look at the number of lines of code in the GraalVM system, there's a lot more code in language implementations than on the lower levels. Because languages are fairly complex to implement, like R, Python, and JavaScript, you all have all these special cases. So it's a lot of logic there. And it's very important for us that we avoid the problem of having to trust those language implementations. But generally, this architecture that we put in place here gives us some additional benefits. When we run those guest language implementations, we can instrument those implementations, and we can use the current tools for managed languages to debug, profile the language implementations themselves. And we make the language implementation process more efficient, because we don't actually need to use a low-level language for running those. In fact, in Graal, like everything is written in Java, so even the lowest level system components. So when I look at GraalVM for databases, I'd like to quickly iterate a little bit why we think GraalVM is a specifically good fit for databases. First one is, of course, ability to adapt to language trends. It's a big problem in the database community that, there are some special languages like PL SQL that would be only valid in the database, not outside. And generally, when you embed a language in your database, you don't want to change your embedding completely if 3 years after a new language pops up, right? So in order, with GraalVM, if you embed GraalVM in your system, you can run any GraalVM-based language, so you can very easily adapt to a new language trend coming up. Second point I already mentioned a little bit on the beginning is because GraalVM can be embedded in the middleware, in the database, and whatever system you choose, you can have the identical language execution on the middleware and the database, for example. It gives you the same performance, it gives you compatibility down to the minor details, and it allows you to reuse developer mindshare across any GraalVM embedding. And finally, as I mentioned before, because of this physical and logical separation of data that's built into the system from the start, we can have low overhead raw data access. So we can avoid actual allocation for objects, we can fake objects, and avoid allocations and marshallings. And there are some long-term trends that we believe will make GraalVM more important over time. I now put out just some statements, so if you disagree with it, please let me know in the Q&A session. But so first long-term trend I think is, data increases faster than bandwidth. You can also see this a little bit when you look at pricing of typical cloud operators. Storing data is usually fairly cheap, but sending data around is where it gets really expensive. In particular, when you want to get your data out of your cloud, that's like the worst scenario. And that's one of the reasons why I think over time it will be even more interesting to send code to the data than the other way around. And in some scenarios, that might actually be necessary, because in some scenarios, the data is so big that you cannot just like send it to another place before you filter it or before you analyze it. And what GraalVM enables here is to run the logic at the place of the data instead of always sending the data to the logic. Because code is easy to send around. It's very efficient. Well, the other long-term trend, as I mentioned before, languages. There's a lot of languages, and I don't think that will change. I don't think the world will wake up one day and say, well, we need these 3 languages, and that's it. Nobody's going to agree on that. More of the software stack is based on external code. I think this is already very visible, where there is a need for access to rich module ecosystem, because you need to be able to run a lot of third-party code when you create your application, which creates this security requirement. And finally, developer costs keeps increasing, of course. Like initially, it was a lot of outsourcing of developers to lower-cost areas. Now we are kind of running out of lower-cost areas to a certain extent. So developer productivity is becoming more important as the costs keep increasing. And we think those long-term trends are actually all playing in favor of GraalVM, meaning they are playing in a way that the GraalVM system as a language-agnostic system to run any language, anywhere, will be more relevant. So GraalVM, to a certain extent, can also be seen as a multiplicative value-add system. So you have the languages on the left, various kinds. Then you have GraalVM in the middle, including maybe some language-agnostic tooling, interoperability, security. And on the right, you have possible embeddings of GraalVM, where the first 4 we have already finished, and we're working on some other embeddings. And there's a multiplicative value add here, because you can mix and match. You can kind of customize your GraalVM-based distribution, because you can use any of the embeddings with any set of languages on the left, and then run that. And in order to make that multiplicative value add very powerful, we're actually inviting other people, third parties, to add your own language or add your own embedding to this ecosystem. Because that would make the ecosystem really very powerful if we not just have our own stack here, but other databases, other data storage, and other languages. And this is why, in general, GraalVM is designed to add new languages and is designed to add new embeddings. We just started with a few example languages, a few example embeddings to get our APIs correct, but we would actually would like to invite other people to join us. And one way actually to leverage GraalVM as well is to write something for this middle part here, because GraalVM allows you to write instrumentations that are language independent and embedding independent. So you can instrument your code, you can create tooling that is independent of languages and independent of embeddings and will work all across the stack. You can create tooling or also research projects on these things. So it's not only extensible on these edges, it's also extensible in the middle with language agnostic tools. Well, people always ask us, well, are you production ready already? Who is using it in production? Yeah, so we are an early stage project. We have some parts that are production ready. We have other parts that are experimental. One part that is production ready is our Java-based compiler, and it's running large parts of Twitter because they get the performance improvements from running with GraalVM. So now some people can tweet faster. I'm not sure whether that's a good thing, but there's a downside to every technology. All right. Yeah, so there's a GraalVM community page, graalvm.org. We are on GitHub open source. The language implementations are all open source. We have a couple million lines of code open source on GitHub, are very active there. So you can look at the code, you can check it out, and you can give us feedback. And we're very thankful for any feedback, positive or negative, or something where you say this is a use case scenario. This is something where GraalVM could be interesting. We're very thankful for any of these inputs, in particular at this stage of the project that we are just about to get production ready. And with that, I am at the end of my presentation. Thank you very much, and I'm open for your questions. Thank you.
All right. How about you choose the...
All right.
I think Graal and Truffle are amazing pieces of work, although I'm worried about Oracle's monetization strategy. But my question is, because I know you've got, you can download the VM, there's a pro version you pay for, and there's whatever. But my question is, we had a keynote about, WebAssembly, and I'm wondering where you see Graal and WebAssembly, whether you're going to put that on top, or whether you are going to run on top of WebAssembly. I know this is way more advanced than WebAssembly, but I'm just wondering where you see that in terms of those two technologies, whether they're competitors, whether they will integrate, whether you have any plans or whatever.
Yes, so we would actually like to run on top of WebAssembly because WebAssembly could give us a way to run GraalVM in the browser. So the main, I think, like our slogan, our marketing slogan for GraalVM is run programs faster anywhere, right? And the anywhere part, the biggest challenge at the moment is the browser. We had some prototypes to create a JavaScript-based backend to GraalVM. The problem is it was 100 megabytes of JavaScript, and the Google Minifier couldn't handle it anymore. So, so we think WebAssembly could give us a way to the browser. And but one of the things that was missing from WebAssembly so far is stack walking, and therefore we couldn't put our garbage collector into WebAssembly. So I don't think it's a competitive technology at all. I think it's something that can create a synergy if we can run on top. We will also support WebAssembly. WebAssembly is pretty simple, I think, to support from our end because we have a JavaScript engine. But I think the more interesting part of WebAssembly for us is to use it to run GraalVM-based languages in the browser. Yes, Peter.
So first of all, this is really impressive. It almost seems kind of too good to be true. So I'm kind of wondering how much are the implementations of languages limited in the sense that if I have a language with a particularly exotic runtime feature, like say first-class delimited continuations, which is something that clearly the GVM is not going to be particularly capable of supporting. Is that something that is going to be really slow? Is it something that's going to be impossible to implement? Or is it something that GraalVM can handle well?
Okay. Yeah, so in terms of language features, yeah, we are a little bit biased towards normal languages like Python, Ruby, JavaScript. They are almost undistinguishable from our point of view. There's some feature, it depends a little bit. Like let's say continuations, at the moment you would need to simulate continuations on your own. I mean, generally, it's definitely possible to implement because you can implement any language feature in an interpreter. That's simple, right? The question is then, how fast will that be? And there are some things that you can simulate in a fast way, but there might others, like continuations, for example, might not be so fast at the moment. That being said, we do have plans to add language features like tail calls, for example. It's currently not in there. We will add that very soon. We might also add some form of continuations. One of the developers, Lukas Stadler, did a lot of continuations work on the JVM. So we do have a patch for the JVM to do continuations. I would say the short answer basically is it's definitely possible to implement it. Whether it's fast or not initially is a different question. It might require some additional runtime modifications from our side.
Okay, we have time for one more question.
Yes, I will be very quick. Maybe we can get the second one.
What's the difference between the community edition and the enterprise edition?
Yes. So so the community edition is fully functional. It has and all of the languages, the language implementations themselves, meaning our JavaScript implementation, our R implementation is fully open source. So at this stage, the enterprise edition has additional performance compared to the community edition, and it has some additional security features. So the secure execution of C code, for example, is at the moment only in the enterprise edition. So you can run your code, but not necessarily with that feature. So in general, yes. So we are like as a company that makes money from licensing software, not from advertising. So that's why we technically should trying to get some license money as well for the project. And but that being said, there is a community edition that's fully open source and it's fully functional. And there's like about 2 million lines of code open source on that project that we maintain in the open. We also are committed to do open source support, meaning if you have a question on GitHub, if you on Twitter, whatever, you do not need any license or support agreement. We will try to answer that. But I mean, yeah, we have also some enterprise customers for GraalVM. Thankfully, we are already in talks with some enterprise customers, which is very good for us because if you get a few of those, the future of the project is very bright. Because like it's a big project. It has a lot of development associated with it. Like the resourcing that goes into the project is very significant. I mean, you can just look at our GitHub commits and stuff, and you will see it's a huge team. So we will need some amount of revenue as well to justify the investment moving forward and to make it even stronger.
Okay, let's thank the speaker again.
Thank you.